Welcome you back to the next lecture on the inorganic chemistry of life. We have been going through some background studies. One of the background study was the biological molecules, biological processes. The other background study that I have explained you is the coordination chemistry aspects. The third component that I need to complete before I go into any enzyme work is what kind of techniques are being used in gauging the biological inorganic chemistry. So, the earlier two components you need to use my slides along with some information from the regular textbook, similarly true with this one too. But this is going to be mostly on the techniques. So, I will not be explaining the physical chemistry behind that or physics behind that, but I will explain mainly what kind of an application is used in is relevant in the context of the metalloproteins and metalloenzymes. Let us look at once this particular slide here. And if you look at this particular slide, there is a huge list of items. There is a list of items more than 1 dozen, and I say that it is not an exhaustive list. So, that means that many different kinds of techniques are being used in gauging the metal ion, its complexation in biological inorganic chemistry. For example, mass spectrometry, some of these you may have heard, some of these you may not have heard also. I will not give much on the principles, but I will give how the utility of these with some example or something. Mass spectrometry, obviously what does it do? It gives the mass of the protein or metalloprotein. When you isolate the protein, there could be a protein impurities, therefore impurity can also be found from the mass spectrometry. Then you will say the impurity is present. The fluorescence emission spectroscopy, what will it do? You have an electronic excitation, but you will not look at the excitation part, you will look at the emission part. So, when it returns back to the ground state, it emits certain light in the form of radiation, and that is what you study, which is referred as the fluorescence emission spectroscopy. In the CD spectroscopy and absorption spectroscopy are very similar, and you know in this UV visible absorption spectroscopy you are looking at the electronic transitions going from the ground electronic level to the excited electronic levels, and that is what is the one which gives the absorption data. And now the same kind of absorption in presence of a dissymmetry or asymmetry kind of a situation, and in such a situation you get the light being absorbed is not uniform. It is absorbed some components are absorbed more than the other. So, generally the plane polarized light can be talked in terms of the two circularly polarized lights, which are referred as the right circularly polarized light and left circularly polarized light, of which if one of the component could be absorbed more than the other, you will get the due to the dissymmetry, and that will give the CD spectroscopy. Therefore, the CD spectroscopy is an extension of the absorption spectroscopy. The feature that you do not see here, you will see in the CD spectroscopy. That will give you the dissymmetry parameters. You can have a negative and positive, and you do not have anything called negative and positive in UV visible absorption spectroscopy. And then when you have electrons in the D shell, some of the electrons may be unpaired. In such a kind of a situation, you will have the electron paramagnetic resonance too. In the organic case, most of the molecules, the electrons are paired, therefore they are diamagnetic. Unless you have a radical, you will not have any PR. But in organic complexes, there are so many metal centers, under certain conditions or the other, the d electron are not paired, unpaired d electrons can lead to the paramagnetism. And you can also try to get the single crystal of these enzymes. In our case, they are the metal enzymes, and look at their atomic positions using the single crystal X-ray diffraction. I will tell you a little bit more details bit later. And there are many other techniques like gel electrophoresis, protein isolation purification, and for ion case we can use something called mass biospectroscopy, which is a nuclear based spectroscopy. It is a gamma ray radiation spectroscopy. The transitions are in the nuclear transitions, not in the electronic transitions. And the fluorescence excited state lifetime, how long an electron sits in the excited state, these kind of characteristics will explain you what the surroundings are. How a protein, when you say if it is a particular group which is giving the fluorescence and there is some surrounding the rest of the protein, how the rest of the protein is influencing that particular species, all this can be studied. You can also study NMR spectroscopy. NMR spectroscopy, what we study in general is called the diamagnetic NMR, but here we can see the paramagnetic NMR too, because iron 2 plus iron 3 plus then cobalt 2 plus, all of these cobalt 3 plus, they have a paramagnetism. The paramagnetism will shift and giving the contact shifts of this. NMR relaxation times can also be used to find the distance between the center and the species which is interacting with it. You can have something called extended X-ray absorption fine structure spectroscopy, which is referred as EXAFS, EXAFS. This will be giving us the information from with respect to the metal center, the primary coordination sphere, but not so much of the other information, not like crystallography will give the entire thing. So, these are some of the things. We can also look at the redox properties of these. So, the electrochemistry with cyclic voltammetry. So, these are some techniques which I would say are absolutely important in this context. Let me see some of them I can explain you with some detail in terms of their application, if not the basic principles of this. Let us look at the first example is the circular dichroism. So, in case of the proteins, what are we interested in? We are interested in secondary structures, tertiary structures, etc. What are the secondary and tertiary structures? We already studied in the earlier classes that there is a alpha helix, a beta sheet and random coil. And you can see that the alpha helix has got this kind of a the CD signature, and if you look at the beta sheet, this is a different kind of CD signature, and random coil, it has a different kind of thing. So, that means now if you take a protein or a metalloprotein and measure its CD spectrum, you can try to identify the alpha helical components, beta sheet components, random coil components. There are ways and means by which you can deconvolute and get each of those things too. Okay, the example is shown over there. This alpha helix has got, these are the kinds of the bands at which ellipticity is found minus, ellipticity is found plus, the beta sheet and the random coil too. So, if you apply this to a protein system, as you can see the different kinds of the proteins shown over here, chymotrypsin is a beta sheet which is having this blue kind of thing, you can see this blue curve, lysozyme which is a red, which has got both alpha and beta, you see that one and these two peaks. So, therefore, giving both the alpha and beta kind of thing. Triphosphate isomerase mostly alpha and beta, and this you can see again very similar to this of this. And then you see myoglobin mostly is alpha. So, the myoglobin is seen from here, as you can see. So, you have different kinds of proteins having greater beta, greater alpha, or beta and alpha combined, alpha more, beta less, beta more, alpha less. All these kinds of things can be characterized by the CD spectroscopy. So, CD spectroscopy is very strong method which will help us to explain the protein secondary structures. Now, when you add some ligand to this particular protein, and what happens? So, what kind of things happen in beta sheets, alpha structures, all this can be identified by the circular dichroism. How will you do that? You take your enzyme or protein, then you add some small molecule or a metal complex or something, and then see that what kind of changes are coming in alpha and beta and random coil. So, you can take as an example, take an apoprotein. How do we get apoprotein? A metalloprotein minus metal ion. What is a minus metal ion? You use some chelator, that chelator can take away the metal ion, then you have a apoprotein. And this apoprotein you take and start adding the metal ion or metal salt or a metal complex, and that will go and sit in that metal position, and that will change certain secondary structures you can monitor too. Let us go to another technique. So, another technique that I am trying to give you here is that single crystal X-ray diffraction. So, for this the criteria is the enzyme should give a good diffractable single crystal. Okay. Single crystal means the whole thing is one single piece and developed along its axis of x, y and z. So, integrated way that it builds in this. So, one of the example is shown here is the lysozyme protein when you crystallize. Very nice faces you can see, it is a nice single crystal, and there is a structure shown here which is a crystal structure, the 30th ribosomal unit, and this is to 3.05 angstrom resolution. I will come to the resolution part in a while. I told you in one of the earlier lectures, the protein data bank will give you the crystal structure or crystal structure coordinates, and then using their coordinates you can build the crystal structure. As you can see here, the 1J5E is a code. This code, if you go into PDB site and give this code, then you will get the structure. Just like you give your the train booking PNR and find the status of your PNR status when you go into the railway website, you get that. And similarly, if you go to the PDB website and give this number, a unique number, you will get the structure. There are a large number of crystal structures are known, several hundreds of crystal structures of metalloenzyme crystal structures are known, maybe to thousands also. Some examples are given: calmadulin, the bracket value is the resolution, is a 3 angstrom resolution, ribonuclease 2 angstrom resolution, tetrainsulin 2.8 angstrom, peptide 2 angstrom, chymotrypsin 2, hemoglobin 1.9, myoglobin 1.9. Do you know whether this number should be greater to have a higher resolution, or this number should be smaller to have a greater resolution? When I ask this particular question in the regular class, I get an answer from many people, the right answer. The right answer is that the smaller the value of this is, the greater the resolution is. How do we understand? I am sure you know that n lambda is 2d sin theta. Okay. N is order of diffraction, then you take this as 1. So n is equal to 1, then this will becomes lambda is 2d sin theta, and d is the spacing, so lambda by 2 sin theta. So this will tell you about the spacing, also is referred as the resolution. So smaller this value is, the better the crystal structure resolution is. So let us look at this table for a couple of minutes, and on the left side column you have the resolution in angstrom: 5.5 angstrom, 3.5 angstrom, 3 angstrom, 2.5, 1.5, 0.77 angstrom. Okay. So look at this. This is the kind of information that you can resolve. At 5.5 angstrom, you can see a overall shape of the molecule, in this case the protein, and you can see some helices are there, some rods, etc., but not very clarity. Then you go to the 3.5, reduce the value of this one, d value to 3.5, means increase the resolution. Increasing the resolution is by decreasing the d value. So how do you decrease the d value here? The d value can be decreased by decreasing this one or increasing this one. So you can increase or decrease. That means lambda, radiation that you used. So you can decrease the radiation that is used. Molybdenum has got the lowest value of the lambda, and increase the denominator. So the denominator is these 2 sin theta. So that means the reflections that you collect should be increased. Okay. So if you increase that one, then you totally d value will decrease. The d value decreasing means the resolution is this. So when you come to the 3.5, you will start seeing the main chain, but not very great clarity. Then you go to the 3 angstroms, you will start seeing each of the amino acid residue. You have seen in the previous class the protein is combined from the amino acids condensation to the peptide bonds one after the other. You can see C alpha kind of things, residues, and that is what it means by. So, if you go to 3 or below, then you will start seeing the resolving the side chains and the peptide bonds, etc. Then you go to the 1.5, you can start finding each of the atom. You go of course to the 0.77, you get very highly resolved. So far there are no structures with 0.77 protein structures, but small molecule structures there are millions are there, 0.77. But for proteins you have the lowest probably is 1.1, 1.2 in the recent days, but not lower than that. So, that means you can get to some extent the each atoms very well resolved, but not to the plus 0.1 kind of a thing. So, how do we understand this in a different in a way? So, it is like let us say we have a huge classroom having let us say 20 rows, and the teacher is sitting at the center near the blackboard, and so you know the first row, the front row will be very close by, the last row is very far, and obviously the way that the teacher can see the last row students is not so clear, but the one below they can show a little better, one front towards him better, and those rows which are very close to the teacher can monitor, teacher can see, observe what all the students are doing with more clarity. So, it is exactly the same. So, as you decrease the d value, the resolution increases. The greater the resolution is, the better the structure is, and that kind of thing one can do that. So, to do all these, the proteins have to be either isolated or proteins have to be synthesized. You can isolate, in fact, a lot of natural resources you can take and then do some steps of the biochemical processes. At the end you can get the protein. Several steps are there, and the protein of interest you can get the structure too if you crystallize, as I told in the earlier. So, there are several steps involved in that. It is not only that, you can take another example too, and you can use the plant source or the animal source, you can get these corresponding proteins out. And in some cases you can also make by using the plasmid. So, if you know the protein what you want, you can generate the corresponding plasmid or the DNA sequence, and that DNA sequence is made into the plasmid, and this plasmid is integrated into the bugs, and then you can generate that particular protein, which is called the expression. So, you can express and get the protein, or you can extract and get the protein. So, the proteins can be obtained either by expression or by extraction in this. So, the proteins, it can be metalloprotein, it does not matter, proteins. So, including metalloprotein. So, these can be obtained either by extraction from natural sources, and it can also be expressed. So, for expression you need to get what is the protein sequence that you want, and that protein sequence should be translated into DNA sequence, and then make a plasmid and put into a live bug and express, and then of course you have to purify. So, purification methods I will explain in a while. Okay. So, protein isolation and purification, as I said, that the proteins can be obtained either from extraction from the natural source or by expression on these ones. The different characteristics, that solubility characteristics, ionic charges, so the protein will have all of these properties, and these properties will determine what method you want to use for either for isolation or for purification. Okay. Their polarity, their molecular size, their binding specificity, etc. Solubility, you can make it soluble, you can make it insoluble by using the salts in and out kind of things. Ionic charge, ion exchange chromatography, electrophoresis, isoelectric focusing, all of these are the different techniques when you have ionic charges present on these proteins. You can use polarity based ones too, adsorption chromatography, paper chromatography, reverse phase, hydrophobic interaction chromatography, etc. So, there are a variety of these kind of techniques are there, again can be used for separating or purifying both ways. Molecular size, so there are proteins when you isolate, there are other proteins also come along with that. So, you need to filter them off, remove them off, take them out. So, this can be done by dialysis, ultrafiltration, then gel electrophoresis, gel filtration, chromatography, ultra centrifugation. So, there are various kinds of things are there. And you can also use affinity chromatography, where your protein will be bound to the column very effectively with some affinity, all other proteins will come out. So, you can do it. So, all these are procedures for purification. So, you can use these characteristics of the proteins both for isolation purpose as well as for the purification purpose too. Okay. One of the example is shown here is size exclusion chromatography. That means there is some sizes are held, some sizes are left out. So, that is what is referred as a size exclusion chromatography. You have the protein which was already isolated by extraction, let us say, or by some other method, and then that particular mixture is passed through some kind of a beads, some kind of a beads, and these beads will have some specific size of the pore. Okay. So, separation of the proteins based on the size is called size exclusion chromatography. So, it is based on the size, and you exclude certain sizes, and the certain sizes proteins are captured. So, small size proteins trap inside, and small solvent space and elute later on. And the large size proteins, they will not enter into the pores. If the pores are small, then therefore you can get these things out. So, the larger ones will come out and the smaller. So, therefore, there is a hierarchy. So, you can separate different sizes of the proteins which are probably impurities in your protein, and they can be separated out, and you are interested in a particular protein. So, therefore, this is dependent on the size principle, and the beads are dependent on the size of the pore principle. So, size of the protein, size of the pore. So, if when the size of the protein and size of the pore are comparable and they are trapped smaller, they are trapped, and when the size of the protein is bigger than that, they cannot be trapped, they will go out. You can see the blue color here and the protein, and that is going out. That means that is bigger than this particular the bead size. So, therefore, that will go out. So, that will basically go out, you see that. So, therefore, based on the size of the protein you can separate, that is called size exclusion chromatography. So, the size of the protein versus the size of the beads that you have, the pore size of the beads having a pore size. Now, you can also purify these proteins by using affinity kind of a chromatography. So, affinity. So, what is affinity? Means it should have the liking. Affinity is liking. So, the more and the more liking. So, liking with what? The protein is liking with the column material. If the column material has a liking towards the protein, the protein and the column material will form a complex and will get retained. Then the remaining will go out. Okay. So, example is the purification of lectins. Lectins have got certain affinity towards a particular specific carbohydrate, and you make a column which is having that kind of a carbohydrate immobilized on that, attached to that. So, such a column you use and pass the solution, then all the other proteins will go out, and only that particular protein will get trapped in that. Only that particular protein will get trapped in that. So, therefore, that is what is called the affinity kind of thing. So, and then use another medium to detach this protein to come out of this. So, you see that let us say this is your column which has some molecule, or it could be, you can call it as a ligand, and this particular ligand will have a specific interaction or specific affinity towards another protein. This is not just a size characteristic, it is a chemical characteristics. So, it is basically a chemical kind of affinity, not just simple size, do not take it as size. The previous one is based on size, the pore or the bead size, not here in this. Please do not take this as a size characteristic, though it is shown somewhat similar to that. So, purification based on the specific binding of the proteins with specific ligands or specific molecules which are attached to the stationary phase. Okay. So, bound proteins eluted with this, etc., etc. So, this chrome protein has got this kind of a protein, this kind of a protein, this kind of protein, this kind of protein, for example. Now, you pass through this, only one this kind of protein will be specifically absorbed and all other things have come out. So, the pure this can be taken out, and this is still retained on the column and then used by elution and then get back this one. So, that is what is referred as the so, you can also have electrophoresis. So, the one is by pore size of the bead, another is by the affinity, this one is by the electrophoresis. What is electrophoresis? Obviously, you are applying a voltage, okay, and you have anodic, cathodic kind of thing. So, based on the voltage, the charge on that, the opposite charge will move towards that, and proteins having certain size, their molecular weight will vary. So, therefore, some of them will move fast, some of them will move slow. So, therefore, moving fast, moving slow under the electric field is called the electrophoresis. So, therefore, you have proteins, different proteins have got different molecular weights and they will make, as you can see, they will come like a bands. So, gel picture showing the pure protein band, and that is the one which you have, and these are some of them cases markers. So, you can identify the molecular weight too. So, you can in fact get the logarithmic relationship between the molecular weight of a protein and the electrophoresis mobility. So, this mobility and the molecular weight standard is known. From this you can find out the molecular weight of your protein too. Okay. So, having got the protein, you can also look at the protein microscopic features. So, you can visualize the small objects at micro and nanometer level using a high resolution microscopes, and the kind of techniques used is scanning electron microscopy, transmission electron microscopy, atomic force microscopy. As this scope of this course does not permit, I am not going into the details of this, but I will show you examples and try to impress you on how well it can be used. For example, scanning electron microscope, this is how the basic configuration of the scanning electron microscope looks like, and we are not going into the details. And you can even micrograph this cell, and that today has come from microscopy, which was not there 30-40 years ago. You can also use transmission electron microscopy, and again this is the configuration of the microscope, do not worry about this. And here this is TM image of gold nanoparticles, and the same nanoparticles can be coated with protein. Therefore, when it is coated with the protein, when it is not coated with the protein, their characteristics will differ. The transmission electron microscopy, which is in short form called as TEM, characteristics will differ. Therefore, we can say that the protein is coated or not coated on this too. So, we can look at another microscopy which is very commonly used, atomic force microscope. In this, in fact, you can get the DNA. See the DNA structure very nicely, you can see the DNA structure. So, on certain surface you have up to about 500 nanometers kind of a scale. So, very nice. So, using scanning electron microscopy, transmission called SEM, transmission electron microscopy called TEM, atomic force microscopy called AFM, we can study the microscopic structures of the protein, protein plus metal ion, protein plus small complex, metalloenzyme plus something else, or protein plus another protein complex. All of these can be studied at the microscopic level, and some spectroscopy methods I will explain in the next class. So, thank you very much.